So, sorry, this is my alarm. Okay, so welcome everyone to session 2 of our Recsys series. Today, Han and I will present the wide and deep learning for Recsys. And then this will be followed by Aditya and Gokul sharing with us their insights about Recsys and its evaluation. So before we start, remember to join our Discord, join the cohort channel on Discord as well, #Recsys series. Please post your comments, opinions, insights, questions, whatever, and subscribe to our YouTube channel. We are also going to share the Google Doc for our notes. Shout out to volunteers from the community, Michael, Siddharth, Ashish. I hope I haven't missed out anyone. We'll be monitoring the Zoom and YouTube chats. Don't be shy. You can unmute yourself and ask questions anytime you want. This is more like a study group and discussion rather than a very formal lecture. So we hope to keep that environment. And also today we are trying to incorporate breakout sessions. And note that you will not appear on the live stream nor be recorded during the breakout sessions. So hope this will help people to speak more freely. Now, disclaimer, we are also learning. Please do let us know if we say something wrong. This is meant to be a study group, not a lecture. Everyone is encouraged to share, ask questions, as well as help us answer questions from your fellow participants and the cohort. Recsys is a rather complex topic. Not every company, everyone is doing it the same way. It also differs by use cases. So we are not saying there's one good way to do it. We're just trying to figure out together. So a quick rundown of the agenda. Han will start with sharing with us the motivations behind using deep learning for Recsys, as well as the retrieval part. I will then continue on to share about ranking, as well as a little bit about the evaluation of the hidden representations of neural networks in general, before talking a bit about cold start problems. And then Han will conclude the session with embeddings. So first breakout session, we are going to give people about 5 minutes to get to know each other. Here are some suggested icebreaker questions for you to get the conversation rolling. And then we'll join the main Zoom back after 5 minutes.
Yeah, so that is the purpose of the breakout, just for people to get to know each other.
Yeah.
Should we start? So yeah, you can talk about anything from including the topic we covered the last time, or just to talk about your what you're working on. Shall we do the breakout room now?
Yeah, can someone help?
I'm gonna do it now. Yeah.
Yeah. Thank you.
Oh wow, this is fancy. How did that go?
That was good. I thought that was a nice little intimate session with Matthew and Sam.
Okay, so try if you like to introduce one of the people that you talk to, who would you introduce?
Yeah. So I talked with Sam and Matthew, and to be honest, we didn't quite get past the first question, which was just about MLOps tooling. Um,
Mhm.
my thing was basically, using some tooling is better than not using any. And then there's so many different things that do very similar. Like there's a million feature stores, there's a million different like inference servers. As long as you choose things that you and your team can support, then like you're probably okay. But yeah, that was just my little spiel.
So what was the
Any,
least common sorry, yeah.
yeah, go ahead.
So who was the least favorite tool?
Uh well, what I said for that was like not using anything, right? Like if you're just like with your
Mm.
bare hands standing up like a fast API or Flask endpoint and like putting them all behind it, like that was where, because I feel like as long as you're using tooling that's not like completely insane or not overkill, then there's just so many different tools and a lot of them do the same thing where you might be splitting hairs if you're like, ah, that's better than that. It's like they're like 95% the same. Like just use something that works and move on.
Okay, fair
Awesome.
enough. So no one put any money on like what company is going to go out of business for the next 2 years.
Yeah.
Okay.
All right. Yeah. So yeah, we have some good comments and questions that came up during our breakout session as well. So feel free to share them on the Recsys chat on Discord. Yeah. Okay, I need a couple more people. So right, let's move on to Han.
Okay, so last session, Chloe talked about like the general structure of a simple two-stage recommendation system. We have the retrieval stage and the ranking stage. And in the retrieval stage, usually we retrieve using some sort of metric factorization-based methods like collaborative filtering or content-based filtering, or using nearest neighbors to retrieve. And on the ranking side, in the good old days, people just build logistic regressions or use boosted trees, or in the case of Google, they use PageRank to rank the results of a recommendation or search output. And starting from early 2010s, people start to explore a lot more about using deep learning to create for both retrieval and the ranking side. And deep learning has a lot of different benefits. First is it learns from the context of the inputs, and it supports a lot of unstructured data, right? Imagine like having turning images into a big fat tabular data. That's just not going to work as well. And it also can capture complex interactions between different elements, and it's also highly modular, so you can use them as Lego blocks. And it also, like really importantly, it supports incremental training, so you can train for one more step or two more steps or just some more new data, and it's going to behave different way. But the difficulty with deep learning recommendation system is that it's expensive to train. It's expensive to learn how to train them. It's really complex, and it doesn't have as much interpretability baked in. So there are some pros and there are some cons. So right now, I'm going to focus on talking about the retrieval side. Next slide, please. And so remember last session that people said, oh, let's do a collaborative filtering between users and items. And people thought, like, why not just extend it to a higher dimensions? And instead of doing collaborative metric factorization, we can use tensor factorization. So instead of just users and items, we can cross users, features, activities, locations, blah, everything together and do it that way. And next slide, please. And the other things that people actually tried is using neural network to do collaborative filtering, right? So they have the embeddings, user embeddings and the item embeddings, and they try to cross them and to get an upper score. So that would be a different way of using neural network for collaborative filtering. And next slide, please. And one of the one of the fun things that's practical reason why people use neural network is that for Netflix, like originally they were using LDA for topic modeling, and after they try to roll out into different countries and geographies, they have to model. They were trying to make the LDA model robust to different censoring patterns. So maybe certain videos has to be censored due to licensing or whatever reasons at different countries. And then also there's also the viewing time of different videos for different users. So they were trying to make the LDA model work using adding different parameters to hopefully capture the latent information. But at the end, it becomes so complex and they have to maintain so many different things. It's just not scalable. So next slide, please. So they tried, so at the end, they they tried to model user preferences using variational autoencoders. So instead of having 200 different models for 200 different countries, maybe 150, then they would have a base autoencoder that creates the user embeddings. They would just continuously train on them and update them for different purposes. And that saves a lot of maintenance work, and it just simplified their processes. Next, please. And the other side of retrieval is using similarity-based retrieval. So it's a method based from information retrieval back in the days when how people retrieve text in documents, right? And usually it's you create vectors that represent an item, text or text, images, or whatever, and you store them in a database, and you can search them by using KNN, like K nearest neighbors. So you can search whatever that's similar to that cluster, right? So I have a search and I can search whatever neighbors it has. Or in the later stages, people, nowadays people use approximate nearest neighbors, because K nearest neighbor is an exhaustive search. It searches through all the similar neighbors, but approximate, it's by definition approximate, so it doesn't search through everything, and it's going to improve your retrieval speed. And there are different tricks that from the computer science side that people try to implement to speed up the nearest neighbor, approximate nearest neighbor search. So something includes like locality sensitive hashing, product quantization, and nowadays the most famous one is the hierarchical structure network search. So you can look up more information online. And when you search, you usually want to search, since it's distance-based, so you want to search by some sort of distance or similarity. And the common distance used are the dot product distance, L1, L2 distance, and Chebyshev distance, which is just taking one part of L1 instead of both. And then there's also similarity search, where you can search by cosine similarity, like how the angular distance between two vectors, or Jacquard similarity, which is commonly used for categorical things that you measure the intersect over union. So that's Jacquard similarity. And one key thing to note is that the distance and similarities, they are not strictly proper. So if you have a cosine similarity of 0.8, it does not equate that it's 80% alike, or they have 80% probability similar. it does not mean that. It just means that cosine similarity is 0.8. It doesn't equate to a strictly proper statistical scoring rules. And now toward the ranking side, and Jim is going to cover the ranking.
Yes, thank you, Han. So let's proceed to the ranking part. So after we have received the candidate pool, we want to have ways to rank them and score them. Typically, we think about it in terms of probabilistic classification. So given a user item pair, what's the probability of getting clicks from a user, or a multinomial given a user, what are the probability of certain interactions that we are interested in happening. And of course, ranking, we can think about it in terms of point-wise, pairwise, or list-wise. And we can also think in terms of relevance. So there's two aspects of it. One is substitutes, the other one is complements, substitutes. Some people also call it similar items. So we recommend something that's similar that can substitute a certain item, whereas complements, some people also call it related recommendation. So if I'm recommending, if the user has chosen a pair of shoes, you can recommend socks, for example. So before deep learning that Han might have touched a little bit upon, so before deep learning, we have statistical ranking mostly, and these work well to a certain extent. There is a lot of feature engineering involved to help make that work. For example, if we take features from a user vector and another feature from a product vector and try to cross them. There's also certain features that might change over time or by certain seasons that we have to account for. So we are not going to go into too much detail into this. Instead, let's consider a use case for recommending apps for the user to install in the Google App Store. This might be familiar to some if you all have looked at the wide and deep learning paper by Google several years ago. So in this case, we have the standard retrieval and then ranking components that we keep seeing again and again so far. And here I'm going to talk about wide and deep learning model, specifically focusing on the ranking part. And to give some context about it, the query can include both user and contextual features. User includes like the country, the demographics. Contextual features can be your device, the time, the location, etc. Whereas another part of our input features would be app impression features. Impression just means what apps we are showing to the user. And the objective is of course to show users things that they are likely to install. So let's go ahead to our, I will call this like a summary of the paper. So here's kind of an example of how we can frame it. We see these different features in continuous values, and then the output would be probability of the app being installed. So when we think about the problem, the challenge and goal is to achieve both memorization and generalization. For memorization, we want to exploit correlations in historical data, what we already know so far. Whereas for generalization, we want to try to explore new feature combinations that we have yet to see. For the memorization part, which would correspond to the wide component of the model, we can add a certain degree of generalization by using features that are less granular. For example, instead of merely crossing Netflix app and Pandora app, we can cross the category of these apps. So video versus music, that would be less granular. But as as you can imagine, it requires feature engineering efforts. And in terms of memorization, the cross-product transformations, which I will also discuss in the following slide, do not generalize to unseen data. But for generalization, we can use embedding-based models to generalize, less feature engineering required. It does complement what memorization cannot do, but then we may also run the risk of overgeneralizing. For example, if a user asks for hot latte with soy milk, or ice cappuccino with full whole milk might live very close together on the embedding space, but it is probably not the right thing to suggest to the user when they are being quite specific. And same goes with niche items. So first we consider wide and deep models separately. We have the wide component, that's the generalized linear model, the deep component, that's your standard neural network. For wide component, one of the main attributes is to have cross-product transformation that adds non-linearity to the model, whereas for the deep component, we have very sparse categorical features, sparse meaning a lot of zeros, and you try to compress them into a dense embedding vector. One memorize, one generalize. And so far we see some trade-offs between the two. So after that, we'll think about how we can bring them together. But before bringing them together, just want to clarify a bit what we mean by cross-product transformation in a wide component. That's nothing difficult mathematical about this. It merely means that we are trying to use the cross-product transformation to bring our attention and focus towards features that are actually relevant. So this is especially useful when trying to capture interactions between binary features. So in this context, we'll just assume that anything with the exponent 0, including 0 with the exponent 0, would equate to 1. It might have different definitions in other mathematical realms, but for the sake of this, we will assume that. And C refers to the learned parameters. X refers to certain types of features, that's binary. So to give a very silly example, in this case, cross-product transformation essentially says anything that is a bear and tame that will return a positive value. And if you can see my screen, yeah, that's my bear. That's brown and tame. And then if I have 0 for brown and lazy, it really doesn't matter because that the learned parameter shows that they don't care about it at all. So like gorilla here, which, okay, it's not very clear with my background, but I think you can see the cream colored bear, that would return a positive label too. So it's very inclusive here. But if whenever we have a 0 in one of the features that we care about, it will always result in a 0 because what you do is just 0, like 0 to the power of 0, that's 1. So you times everything together, it equals 1. But then if you have you are missing something that is relevant that you really want to pay attention to, and that would produce a 0, and you multiply everything together, it will result in 0. Now, we move on to the embeddings, part of the deep model that I mentioned. So if we look at the indicator column, that is probably one hot way to represent like many different input examples. So like a dog is probably not a spoon. So you can imagine how many zeros we have just to kind of represent certain things. But then if we can turn that into the embedding column, this is essentially like a set of coordinates that points out where a certain item we are trying to represent lives. And one important thing to note is that sometimes the absolute value of the embedding isn't as important. What's important is the relative position of one embedding versus another that describes its relationship, as we can see on the right side of the diagram. And remember, I talked about overgeneralization. From here, we can see mathematically why it can overgeneralize. So here we have a lot of zeros, but here on the left side, we see the embedding column that has real values, non-zero real values. That means that there may be cases where an item user query, we expect there to be no interactions whatsoever, but it still generates a certain value to it because of these non-zero values. Intuitively, we can also think of it as embedding vector being just a form of compression, compressing very sparse data like this into a more compressed form, and hence we get some spurious results. Now we're ready to combine them. In the past, people have tried different types of ensemble models where the individual models are trained separately, and we only combine their predictions at inference time. That means that, in a sense, each individual model needs to be sort of standalone, that it needs to be large enough to be accurate by itself before generating something useful to combine those predictions at inference time. What Google proposed in their paper is to optimize all the parameters, both in the wide and deep parts, and the sum of their weights simultaneously during training time. And we don't need the wide part to be so full size, because all it needs to do is just to cross certain features that we need to complement what the deep model doesn't do as well. So moving on, I'll discuss briefly about the implementation part. They presented three rough categories: data generation, model training, and model serving. In the data generation part, we can see user data and app impression data going into the training data generator. For vocabulary generator, it merely means that we are taking string features and mapping it into IDs, numbers, integers that are easier to handle. So I think I've roughly talked about this. So let's go on to model training. So how they train their model is that the embedding vectors are first initialized randomly, and then they train it to minimize the loss function during model training. And as a side effect of training a supervised machine learning problem, the model can encode these categorical features into embedding vectors. When they train new data, instead of initialize to random values again, they actually take the embeddings and linear model weights from the previous model. So in a sense, it's a warm start when they get new training data. We can see in the following that the continuous features like age, app installs can be plugged into the deep model directly, whereas the categorical features, we convert them into embeddings before plugging it into the model. But at the same time, these actually go into both the deep and the wide part of the model. The wide part takes the cross-product transformation, and they try to minimize the logistic loss function. They didn't discuss too much about model serving in the paper. It's quite standard. They retrieve a set of candidates to score, and then we rank it from highest to lowest and just pass it through, just a forward pass through the model. As a sidetrack, I think Aditya and Goku might cover a little bit more about evaluation, but this is just something I found while researching the topic. And when I read about deep neural networks, I always find it like a sort of black box. Like I don't really know what it's doing inside. I know that's the input and the output, and then things seems a bit mysterious to me. So I found this paper and talk about the evaluation of hidden layers in the network. That's a CKA. I wouldn't go too much into the math and calculations and stuff, but just for general intuition, it tries to ask the question: does layer M learn the same thing as layer N? So, for example, here we are just comparing different layers and creating a heat map. The CKA calculates the a scalar similarity score based on those different layers. I've included the papers, blogs, and videos for people who would like to learn more. They showed here that when the what happens when the model gets deeper, and what happens when the model gets wider at the second row at the bottom. So as expected, we have this diagonal line of really bright yellow. That's because you are comparing the same layer. It's obviously similar. We have this very bright block structures that's trying to tell you that you can actually prune off a lot of these layers because they are so similar and it adds nothing from one to another. So do wide and deep models learn images differently? So this is a bit different from our Recsys problem, but I thought I'll mention because they to take inspiration from a different domain. They took like a deep ResNet comparing with another deep ResNet, but I think they have a different initialization or seeds. And then for the blue ones, they take a wide ResNet with a deep ResNet and make the comparison. So in the end, they found out that there's a difference between how they learn. Although the average accuracy is the same, but the deep part learn objects better while the wide part learn scenes better. So I thought how models evaluate based on how the difference of the models perform based on class is quite interesting. So we are not just looking at the average accuracy. Now, almost the end of my part, but I'll run through some matters about cold start problems. Cold start problems, as we know, when you have new users or new items, it might be difficult. Very commonly, I guess for new items, it can be a bit easier because most of the time, if you have an item on your platform, you have a lot of site information, metadata about the item. If you have new users, it's up to you to try to fish them to volunteer some information about themselves. But you do still get a little bit of information to get started, hopefully. Now, the second point is something that I'm quite interested in because say if you have a new user, you can also look at implicit feedback, things like clicks, browsing history, or you can get more information through external sources like data from trackers. I'm not condoning it, so put an evil emoji. It's, I don't know, ethically. So you can get it from social media accounts if they give you permission to do it, but also, I don't know. What I'm excited about is having real-time infrastructure to support it, because then if we can learn and train online and and online learning and training, not just online inference and prediction. I think the former is quite tricky to do, but it's very important, because if you get some feedback from the user and you can use it to train immediately, then you can respond to what the user is telling you more quickly. Of course, there are other methods like popularity based. Maybe you just simply recommend something that's popular within the demographics or age group. It can be something random. I think sometimes random might be an effective way to do it quickly. I've also heard of people who mentioned using autoencoding to generate embeddings unsupervised at the start. I've also heard multi-arm bandits being mentioned quite a lot these days. It's more of more related to like the reinforcement learning realm, where you try to maximize rewards by considering both exploration and exploitation. I won't go too much into that detail, but I think it's a good time to pause for questions. And MAB is the way to go.
I'm very big on Bandit.
Yeah.
Yeah.
Would you like to share a little bit about it? Because yeah, I haven't done too much research about it, so we might benefit from your views.
Okay. Wow. I'm glad you asked. I'm just like waiting for an opportunity to talk about it. So are you familiar with contextual bandit and A/B testing stuff?
Mm-hmm.
Yeah. So contextual bandit is, I can think of like smarter A/B testing. I'm not sure if that's just IL people would agree. So A/B testing, when you route traffic to different models, it's pretty much random. So you can route, like when you receive a prediction request, you can route it to model A and model B without knowing how each model is performing. So you can do that like so you don't need to know the state of each model. Whereas with contextual bandits or multi-arm bandit, you route traffic based on how each model is performing. So which means that you route traffic based on like which model is going to give you more information to decide. So that's why the multi-arm bandit is a lot more data efficient. Because there have been like multiple research like just show that in a certain context, multi-arm bandit is actually optimal way to like evaluate two model against each other. But however, it's hard to implement because with A/B testing, you can route traffic without calculating the model current performance. So it's just like pretty random. You don't need to know how each model is doing. But like with multi-arm bandit or in this case contextual bandit, you need to know how each model is performing before routing the traffic. So in a lot of companies, they don't really have a good way of like computing model performance on the fly. So that's why they can't implement it. But yeah.
Hey, this is Anji. Can I add a couple of things on MAB?
Yeah.
So I ran some marketing campaigns on Facebook, right? Advertisements. So when you do that, they will ask you to give you more than one version of the advertisement that you want to place. So then we gave like 2-3 versions of the same ad with some minor variations. Now, when in the first 1 hour, we got like, multiple clicks for one version, then the second version, they're kind of evenly distributed, right? Then we came next day and we saw 90% of the ads went to one version and rest of them went to other ones. And after that, the only one that had highest success rate, only that got the clicks, right? I mean, that got shown to the customers. So bottom line, right? I mean, I think the Facebook and Google's and they looks like they have a very good infrastructure for implementing MABs. So they take give the versions that you give to them and they show it, and whichever one is working, that gets shown and rest of them get discarded. So that's one way people would use it.
Yeah. So you're saying that you are using contextual bandit to deciding which ad to show to users.
Right. I think Facebook algorithm takes care of that. I mean, you create the 2 or 3 versions of the ad, and depending on which one is getting more clicks, the Facebook or Google keeps showing the same ad as opposed to the other ones.
Yeah. So you're saying that so after the first day, the next day you come back, you realize that most of the traffic is gone to one ad.
Right.
And the reason is that the multi-unbounded algorithm decide that that is the most optimal way to show ads to user.
Yeah.
And is that a good thing or bad thing?
I see from a Facebook point of view, it's a good thing, right? Because they are getting paid for like clicks that you are getting. Now, but is it good for me? I don't know, right? Maybe it's not a clickbait, but the other one may be more useful for other people, but that won't even get shown. So from if I am paying for it, it's not good for me. But if I'm getting paid for it, I guess it's
yeah. So I think like one thing I'm big on Control Bandits because it reduce the opportunity cost, because when you A/B testing, right? Because the less you're unsure about which model is better, the more likely that you're gonna show like the bad model prediction or the bad ad to user. But whereas like the multi-unbounded, because it's more data efficient, which means that it can determine which model or which ad is better. So it's less likely to show users the worst version of it.
Yeah.
But it's hard to implement. It's like really hard. And I think people need to wrap their head around, as in people are very much using like a randomized trial experiments as the best, but then multi-unbounded are not randomized. So in that sense, this is like, why do I use it? It seems weird. Like if you wake up the next day and see that 90% of the traffic goes to one, it's like, how do we convince that it's the right thing to do? But yeah.
But for MAB, there should be good tools out there, right? I mean, no one. There should be. I mean, this is a complicated process. So, are there no good tools out there in the market for implementing MAB experiments?
So to do MAB, you need to take control of the bridging service, because you need to do two things. Like you need to like have a way to route traffic and then show the predictions to users. And second, that you need to find a way to calculate the model performance right now. So that means that the tasks have to have some form of natural labels built in, like for example, like click-through rate, like ads or recommendation systems that you need to join user click with the predictions, so you can compute with that on the fly. So that I think like I'm not sure like there are tools out there, because it wouldn't require a lot of integrations with the prediction service, and has to ingest click streams so they can extract labels and then join the labels with predictions.
Yeah.
And I think one thing that's important is that most people don't have enough data to support this type of things, right?
Yeah.
I mean, a lot of it is, Thompson sampling, MAB, or UCB algorithm, all this things works really, really well theoretically, but do you have enough monetary incentive to support this type of infrastructure? Because it's not only on the model evaluation side, it is also on the core infrastructure side. So imagine you have to have you have to, your KA cluster or whatever cluster, sometimes it's even hardwired, has to be able to support routing this type of traffic to different models on the fly. And it's not just only one single model. You could have multi-unbounded on many different places, and that traffic routing just becomes crazy. And also you have to somehow reset some of the, maybe if you're using contextual bandits, you have to reset the state once in a while. And how do you reset the state? When do you reset the state? And I don't think most companies have that type of thing to capture everything. And as Chip mentioned, you cannot optimize. You cannot use bandits to optimize for certain things. Especially when you have delay label, right? So you can optimize for click-through, but you probably cannot optimize for convert, or you cannot probably optimize for GMV or return rate or other stuff, just because you do not have live data coming back in. Click is really easy. It's one of the easiest data to get, but the others, it's pretty hard. But yeah.
Yeah.
Can I add just one quick anecdote, which is, what you said, Chip, about updating for AMAB in real time, like that that is like really, really hard to do. And then we did some, like in my company, we did some studies like, okay, if we were to actually do this, like really try and update the model for the Bandit, how much lift would we get? It turns out that it's just, if you compare it to like the statistical noise for a customer to really figure out like, okay, I'm actually seeing a measurable lift, it's not worth the effort. So instead we just kind of have a bit of a stale data, just use the data from yesterday and, just do stuff, and it works just okay. Yeah. Sometimes you have to really consider that, the weigh those two options.
Yeah, like when you do power analysis, you end up needing a lot of data, a lot of clicks and data to capture like 0.1% lift on one thing to determine if there's actually any lift. So I haven't worked. I don't have the opportunity to work with that much data. Maybe perhaps someone else had, but yeah, it's different.
I think it's a classic chicken egg problem. It's like when you have some new things, it's like theoretically it can show a lot of improvement, but then you need to require a lot of work to do to see the improvement. So like it's just like so you need to do a lot of work first to see improvement, but then you also don't want to put in a lot of work until you see improvement. So it's hard, and I do think that what really bothers me is that like a lot of companies are very insistent on like controlling the patient service, because it was like, I think like because of literature like tools out there saying that deployment is very easy. You can just like package the model, push something on endpoint. Now you have a patient service. But like to do patient service right, it's like a lot of work. Like to have all this like experimentations built in, A/B testing. A lot of companies are not even doing A/B testing right. So I feel like multi-arm Bandit is very far out. Like it's a lot of people like A/B testing, they don't even wait until they have like significantly what is the term? Statistically significant result. Like this is like run the test for a random amount of time, and they were like, okay, that sounds about right. Now let's switch. Like it doesn't, like they don't even do it right. So
I just doing it for the sake of doing, right?
Yeah.
Okay. I think before we end the session, we have a breakout session, and Han will talk a little bit about embeddings as well.
Well, I think in the interest of time, let's skip the breakout and we'll just go dive through embeddings. Yeah. So embeddings, like we talk a lot of things about deep learning, it's about embeddings. And what is embeddings? So in the good old days, it was basically any vectorized representation of an object. It could be text, image, product, item, graph, whatever, or temporal events, right? Any vectors that represent an object, it's an embedding. It basically maps from one space to another, right? So that's the technical sense of embeddings. Of course, this is using the definition very loosely speaking, since we're doing machine learning, nobody cares about math, right? And back in the days, and in the late 80s, people already started to use vector space models. So people represent a passage using TF-IDF into embedding. And then there, around the same time, there are also latent space models. Latent space means that the space it's not observable. So people converge using metric factorization to learn a vector representation of certain text and passages. And one of the most famous one is LDA by Professor Andrew in 2003. That's used for topic modeling. And starting in the early 2010s, after Google came out with the paper Work2Vec, and it basically learns a vectorized embedding for a single word. And this is all attributed to deep learning because it is able to provide the flexibility to learn from different data structures and its capacity to do contextual learning for embeddings in different space. And one of the research subject is called representation learning, which is basically how to learn embeddings. So on the right-hand side of the chart, of the slide, you can see that Netflix creates embeddings for their movies and they map it into a 2D space. And you can actually see like different type of movies tends to cluster with each other. This, obviously is a very good example, but sometimes things don't cluster as well. So that depends on how you train the embeddings. Next slide, please. So there are many ways to generate embeddings. One of the fun way is you encode every session, and then you train, you encode every session, and you treat the sessions as a recurrent, as a sequential event, and you can use RNN to learn the relationships. And next slide, please. And after Retrieval came out, people came out with different ways to embed users. So people created user embeddings, and sometimes people also use product embeddings in Retrieval. And some crazier things that people did is they embed users and items together and do a joint training using a sysytems network. Next, please. And one of the way that in e-commerce that people can train or train embeddings to recommend the next relevant item is that they train that, say, for example, have a shoes. I try to predict, what's the next thing to recommend. People might need a pair of pants or shirts or jackets, etc., using a recurrent model, using LSTMs or attention-based LSTMs. And this tend to work well for fashion. And next slide, please. And then there's also models, sysytems models that try to train embeddings to know which two items goes well together, right? So this is going to help people to discover new things that might pair well together when you dress, or when you cook, or when you do like different things. So this there are different applications. And next slide, please. And on the other side of the fence, you can also turn problems into graph, into computation, or into graph problems. So maybe you can set your node and edge definitions for graphs, and you can train graph embeddings. Next slide, please. So in the example of Pinterest, so Pinterest is a image-based social network, and so for every pin, whatever called, that's what they define as a unit of thing that you view. You have the image and you have the text, and a user can collect a lot of different pins in a pin board. So to model this type of interaction, to decide what to recommend a user next, they create a graph convolutional network to learn the associations of the whole pin graph. And there's a paper right here. You feel free to dive in. Next slide, please. And actually two more things that's super important. Right now, up to now, we're talking about how to optimize for user. Everything is very, very user-centric. But in certain use cases, you might want to optimize not only for the user, but also for, let's say, in the example of Uber, you would want to optimize for the seller or for the driver, or in the case of eBay, you might want to optimize for the seller as well. So it becomes a multi-objective problem. So instead of just finding the best policy for the user, you have to find the best policy for both the user and the sellers, or it could be like it could be a lot more complicated than just doing a very user-centric Recsys. And the other thing is, instead of looking at just one single box, one single widget on the website, another active research area is how do we optimize for the whole page instead of just one single widget. Right? So that's another research area, or another subject, another area that people are actively looking into. And next slide, please. So here are some references. So I think in the interest of time, do you guys want a quick break before we introduce the next session, or we should just dive right in?
Do people need a break to get tea, or should we dive right in? See, I like the enthusiasm.
Yes,
definitely.
Yes.
We will share the slides. Yes.
Goku, you ready?
Yep, I'm ready.
No goes like I'm born ready.
Yeah, maybe we'll take a break after this one before we start the next one. But there are some really nice discussions happening on the side too. So I was reading up on those. All right, so in this section, we decided to join it with this because I think it'll be a little bit shorter. And then so next week we can do the final jam session. But here I'll cover just sort of high level on some of the design decisions around recommendation systems. And then Aditya will go into details around evaluation, sampling, into a lot of the details of the content that we covered so far. All right, so this is session 2.5 technically. And then the next one will have the session-based jam, which will combine everything that we learned so far for a very specific context. And I think that'll just make it a whole lot easier to see a lot of these topics that we discussed firsthand. And then it's going to be a separate video on YouTube. So just going to go over this again. We have the Discord channel to talk about all this, specifically the Recsys series channel for this specific topic. And then we just started the YouTube channel to host all these videos so people offline can learn about all of this. Google Docs, which I think several of you are helping to maintain, and a lot more other resources here. And then there are a few terms that we'll be covering as well. I'm by no means an expert. I don't really think anyone else is here as well, but we're all learning here and we're on our way to becoming experts, hopefully. But even I am happy to see a lot of other people here in the audience here. I'm going to be talking about design, but I just saw we have Manoj here, who's probably one of the best ML architects that we have here. So feel free to chime in, correct us, and we'll definitely make changes to the slides as required. And some shorthands as well that we'll be referring to, which I think we reviewed. Okay, so I'll quickly cover the design aspects. I think last week when Chloe gave her presentation, we distilled it into 4 distinct steps. Retrieval, which is really about using our catalog of items and then whatever the user may be interested in, whether it's a query or a specific item, and using these 2 facets to generate your top candidates. And then the object filtering, basically to reduce from that list to take out items that you may not want to show, and then using information, hopefully, as real time as possible about the user and the item categories to score each of our candidates so we can rank them. And then having some additional policies around ordering so that we can come up with a final order, which we're going to use to show these on the UI, render them on the UI. So next slide, please. So for each of these, we'll have different infrastructural needs and design considerations. But sort of the foundation is where all of this data lives. And there's so many different types of data that are involved here. And during the jam session, we're going to be talking about each of these in detail for a specific context. But I'm just going to list out sort of kind of go through a bullet list right now. But I think there's different names for this, but we'll just call it logs for now because a lot of the papers refer to them that way. But something like a user click history, you definitely want to track this. You definitely want to store this in a very robust way. And I think a very quick and easy way is to throw this into like a data lake or an object store. So S3 is a very common option. Some of the larger companies I've been seeing, Hadoop be a very regular choice. We'll see eBay use Hadoop here. Hashtag abolish Hadoop. And then we have sort of the near real-time events. We'll cover this for some of the more real-time use cases, but you have separate infrastructural needs here around data streams. And you also have separate tools for actually doing the processing on these streams as well. And then for specifically items in our catalog and things like that, you can use traditional databases. A lot of them have different advantages. I think in the eBay paper, we'll look at in a little bit, they use Couchbase, so key value. It's also a document type of database as well. Postgres, normal choice. And they'll do a lot of the filtering and things like that like out of the box for us. So a lot of considerations there. And then this is not necessarily a specific type of structure here, but to be able to train our models and to be able to fetch features without skew and things like that, feature stores are a common consideration here, both the offline and online consideration. So a typical stack you may say here is BigQuery, the data warehouse, which is a type of database, but used for sort of aggregate analytical use cases. And then Redis may be your online store for low latency. All right, to the next slide, please. Okay, so I'm just going to go through each of these in a little bit more detail, just so we can have a little bit more context. But for retrieval, in the offline phase, we're going to need to learn how to represent the items in our catalog. And obviously, this will be painted much more clearly when we have a specific use case next week, but just a few different ways this happens. You don't necessarily need to have labeled data here, right? You can have sort of a sequence. So maybe the way user has interacted with a certain item, you can use these sequences to train, skipgram, bag of words, et cetera, to learn these embeddings without labels. You can also, it's not just about items, but maybe the user searching with a query. So this could be text. You can use, things that we've been using for pre-trained embeddings for text. It could be, Retrieval, glove, whatever you want. You can also train on top of that as well. And then certainly for the user, maybe if you're a very large corp, you have more sophisticated ways of representing users, more specific ways as well. But you can also represent users maybe through not the user ID themselves, but maybe through their actions or the categories they're interested in, and use those embeddings and concatenate them or average them together. A lot of unique ways. And I think every paper that we've seen so far in prepping for this has covered sort of unique ways of generating the embeddings. I think maybe a universal aspect here is they all constantly try to relearn them as I think Chip mentioned earlier, as context changes. And you want to be able to do that because they could become stale, especially if you're in a very fast moving area. And then in the online scenario, you want to be able to obviously use that model to embed, whether it's a user query or an item that the user clicked on. And just to show what this would look like, right? If the user is searching for something, you want to recommend the items that are relevant for that search. But if the user is clicking on something, you are generating items maybe that'll populate the side tab or something like that. On Amazon, you see that a lot. So this is what we mean by embedding the user's input here. For infrastructure here, this is like any other model. We need to be able to serve this. You want to do this in the beginning, maybe ad hoc, but eventually you want to use a very robust server for this. We'll talk about Triton at the end as NVIDIA's example, but you need to have the capabilities of versioning, rollbacks, updates, et cetera. And then if you're at very large scale, you want to be able to have a lot of the components that will handle that scale, like load balancers and robust APIs. All right, next one. So once we have, you have the embedded input, and then you have your, list of items in your catalog that have been embedded, you want to be able to figure out the similarity between them. So here, the approximate nearest neighbors index that Han talked about, there's a lot of options here, right? I think popular ones are phase, annoy, scan, NMSLib. I think, or at least from what I've seen, a lot of people will have this built as a standalone service and then have that be deployed. But there's this increase in a vector database, or also VSS, vector similarity search, that are coming out of the box from a lot of companies. So Redis, I think that's like their flagship product over the last 2 years, VSS. But there's also a lot of smaller startups that are coming out with this Milvis, Pinecone, just around being able to do processing around vectors, similarity and clustering being a few of them. But a lot of options there as well. Next one. And then for filtering, I'm not going to go too deep here, but basically, it's when you think about it in a small scenario, you have your top candidates, and then maybe you have some subsets of things that you want to filter for. So, if it's someone under 18 searching for something, maybe you have a list of items that are mature. So you're going to check every item in your candidate list with that subset. But imagine as your subset grows, that's a lot of database queries that you're going to need to run to check every single item. So filtering, I think, has been made quite efficient with this concept called Bloom filters, which I think is actually from the 70s. But today, a lot of databases come with these filtering operations out of the box for us. And I'm not going to go into details here, but effectively, anything that we want to check to see if it's in our database, without actually querying the database itself. So they'll hash the input, and you can check to see if that exists in the database or not, but it's not exactly exact. So you can know for sure if it doesn't exist based on the filters, but if it does exist, you'll go further down the pipeline. So you may have 10 filters, and then finally you may need to just make the call to the database anyway. But at the end of the day, we'll be making far fewer calls to the database. And it's just that's going to be a major factor when we have very large spaces to be checking for. And a lot of databases come out of the box. Cassandra is definitely one of the popular ones here to offer these out of the box, and Postgres as well, I believe. All right, next one. So we had our top candidates, we filtered some of them out, and now it's about, for each of the top candidates, we want to know what's the likelihood that the user will interact with it. And the interaction could be a click, a purchase, a like, whatever you want. And you want to be able to learn a model, train a model to be able to predict this likelihood score. So to be able to do all of this, we need to have relevant information about our users and about our items. And this is where the concept of feature store comes in really handy, because we want to be able to do certain things with certain constraints. So one of the most important things here is whether it's for training our model or during the online, for inference, we want to make sure we generate the features in the exact same way. And this kind of skew, if we introduce it, can throw all kinds of errors. But something like using something like a feature store can definitely help with that, because it's a single source for how the feature is generated, and then you can retrieve it from there. Also for training and for inference as well, you want to have the most up-to-date feature values. And again, for the real-time scenario, this becomes very important, because as soon as certain events happen, you want to be able to register that and fetch those features because you are in a very fast-moving space. And then for training, most of these stores come with these features out of the box, like point-in-time correctness. You shouldn't introduce data leaks when you're training for this, because then when you actually deploy these things, you're going to have not so great performance. Next slide. And for the feature store, I would say the two main kind of storage considerations here are the offline store and the online store. This what I'm showing right here is kind of the batch version, where we can fetch historical values for training, and then the features will actually materialize to your online store. But when we look at the real-time scenario, I think it's on the next slide, Aditya. I think was one of them skipped, or okay. I think I'll go back to I'll go to the real-time one after this one. But in the real-time scenario, you'll have sort of another processing here for processing the events, doing the stream processing, and then sending the features to the online store directly. All right, next slide. So once we have a very robust way of fetching the information about our users and the items, now we can actually start to construct the model and then also use it for the online scenario. And so one of the main tasks is to predict the probabilities for a certain event. And usually we'll have the features about the user. We'll also have the given item that we're trying to predict the likelihood score for. So this is from an Alibaba paper. They basically represented the user or the user's features as the events that have occurred with the user. So this is what the user has been doing, and so that's the input. And the final part of the input here is the target item itself. And using the trained model, you can basically just slap on a sigmoid at the end, and you can get the likelihood that the user will interact with this item. And you do this for all the items, and you effectively have scores to use to rank. And then finally, on top of this, so this right here, this model is very similar to the embedding model in that it needs to be served in a robust manner, and you need to be able to maintain that. And then the last piece here is the ordering. This is usually just business logic. I think we've seen it written as just simple policies. Again, it needs to be in a separate place that can be updated and called upon, but it's to rank the candidates beyond just based on the scores. Maybe you have some external logic that you want to throw in, like novelty or randomness, or whether the user likes new things, etc. Okay, and then next slide, perfect. I think we're okay on time. And then for the big difference here for the real-time processing piece is that there's this additional infrastructural needs around consuming the real-time event data through your streams. Kafka, Kinesis are popular options here. And then being able to do the processing on these streams. I think Flink is actually, I've seen, not just in the eBay paper, I've seen it very widely used. And you want to be able to do this so that you want to, usually we see it in this case here for generating the user embeddings. Instead of doing that in the offline scenario, you want to use the most up-to-date values, features for the user to be able to generate the embedding. So you have the recommendations that you're generating are super relevant and are super up to date, taking into account maybe something the user did just moments ago. All right, perfect. Next one. And this is just like a sort of a deeper look into the eBay paper, which I linked in the bottom right here. The left diagram is their fully offline version. And of course, they started offline. Then they actually went to an offline plus near real-time hybrid, which is a second image. And then the final one, they actually use the sort of the data streams and Kafka to do the fully, or still near real-time, but no offline processing at all. But on the left here, they have, Hadoop is their main database here. They have this, they have a separate GPU cluster to do all the processing. But effectively, they will make the recommendations for a specific user ID offline, and then they'll store it in Couchbase, which is a key value database. And then in the online scenario, the recommendation application will simply just pull from this database. Now in the hybrid here, basically they still generate the user content offline, but this time it's not the recommendations, but the user embeddings. So for every user ID, they'll represent the user somehow. But then in the online scenario, a specific user ID will be coming in, they'll fetch the embeddings. The user embeddings go to your KNN application, the item embeddings are also there, and you get back the results. So instead of having the recommendations be generated offline, recommendations are now online, but the user embeddings are still offline. In their fully near real-time example, the user embeddings, which we saw in the last slide, the user embeddings themselves are also done in the online scenario there. Perfect. And last slide, I think. So obviously, these are a lot of infrastructural considerations. And right now, I think a lot of teams are building this stuff out themselves. But I think in the last just few months, I've worked with companies, small startups that are trying to do this in a more packaged manner. But you also have larger companies who are making offerings, open source offerings as well. This is Merlin and Triton from NVIDIA, where each of the different processes we talked about, even feature processing and transformations, when you get to large scale, you want to do this in a very efficient manner. So they have NB Tabular to do this using the Rapids library. They have a huge CTR, which is for click, they named it after click-through rate, but you can use it for training the embedding model with caching, parallelization, all the things you need to do this at scale. And then for serving, they have a very robust option, not just for Recsys models, but they threw it in with this stack here because it makes a lot of sense to offer this at scale and orchestration to control all of these different processes as well. But I think next year, this time, we'll probably have a few more robust options out there as well for doing all of this in real time, batch, whatever it is. But yeah, quite a few infrastructural needs, which is why I think, which is what makes this problem very difficult to apply in industry. But this is just the infrastructure side. There's a lot more on the evaluation and sampling side as well, which I think should be thought about long before we get to the infrastructure. This is like getting to the building side. And it's really important to make sure we're thinking about the design of the problem without the infrastructure components first. So Aditya will go into details about evaluation, which I would argue is the thing we should probably start with as well. Cool, should we do a small break here for people, or what do you guys think? I think Aditya's will be around 20, 25 minutes as well. And then should we have discussions afterwards?
I would say that we should have at least a minute break so that people can digest all the information that we have just shared with them. So, but it's open to people. What do they want? Should we just continue with the evaluation side, or it's okay to take a minute's break, pause? Hello.
I could vote. For me, it's fine going. I know that we are a bit out of time, so I'm down continuing.
Yeah, looks like people are saying, let's go. Okay, perfect. There's a lot of energy on a Sunday. Or I guess Monday, maybe for some of you.
All right.
Yeah,
So
yeah.
Please.
I know it's like really like a Goku session slides on like online streaming processing. You know, I guess I'm very biased and very big on. I'm a big fan. So.
Cool. So we are at the last stage for this session, actually, before we close. So we would just like to talk about evaluation here. And we'll not just be talking about what exactly evaluation for recommended systems, but for any system in general, evaluation is a critical piece, because that is the only way we can say that our system is actually effective. It is actually doing what it's supposed to, right? So let's go and let me just share like the general problem with the evaluation. So this is actually not just relevant to recommendation system, it is actually applicable for any ML system or any system in general. So what we actually care about from a system point of view, because everything is business related. So there are definitely going to be business KPIs. Then there would be lots of long-term sales predictions, user satisfaction, trust, happiness, and things like that. But what we can actually measure from our system, and I would just repeat it itself, that it's not really very easy to measure. So we can only measure short-term sales, because we cannot really measure or do projections on long-term sales or take like months, weeks, and more than that. We cannot really do forecasting like that. Apart from that, we also can measure ratings, we can measure clicks, latencies, your stress, whatever you want to do on your system. That can be measurable. We can do all this. And then obviously there are typical metrics, predictive accuracies, and etc. Apart from this, actually, what exactly makes evaluation complicated? Because a system is made up of multiple components, right? And it's not like that the same team is handling the whole system together. Different components are being taken care by different teams. So in addition to all the teams, I would say that it makes evaluation much more harder, because we don't know exactly how to evaluate the whole system as a whole, right? Just to motivate actually with respect to Recsys, let's say, before we go to the next slide, when we're interacting with the Recsys system, we usually have something like a user intent, because we want the Recsys system to capture that. By user intent, I meant that what exactly is the user trying to search for? How specific they are in their search. So for an example, did I mention that I want to search for an Apple iPhone 13, let's say? I have mentioned the brand, I have mentioned which version I want. So I'm being very specific here. Apart from this, user context would also be important. By user context, I would say that how comfortable is the user with the platform? Is it something that, let's say, every one of us visits Netflix, so we are pretty much very comfortable with the UI which Netflix offers, right? So we don't actually need to use its recommendations. We know exactly where to search, what to search for. So we can straight go away and search, and we can find and start watching. For an example, apart from these two things, user intent and context, the third thing is how exactly is the recommendation being presented to the user, the UI point of view. So Netflix usually has a strip of like 10 videos or 12 videos, which you can just scroll on the right side. But if you will go and look at TikTok, you get a full screen UI view, which is something very different, because now TikTok is actually placing a lot of bets on every recommendation on every video which you are seeing, which is very different from what Netflix is doing. So it's not really the same thing. Bottom line is you cannot evaluate different systems using the same metrics or the same set of questions or metrics, whatever you want. Apart from this, let's get into evaluation of recommender system specific. By now, I am pretty sure that everyone here is convinced that it's not really easy to evaluate. Proper evaluation is definitely important, but it's not really easy to do it. Why is not easy? Let me just give you another example right down here. You can see that if someone clicks on an item, so do we exactly know that the user is clicking because user likes that item, or it is just because the item was just being recommended to the user? We cannot actually know for sure why the user click was made. Apart from this, actually, there are some metrics which can influence your results as well. Like what exactly is your choice of metrics? It can actually deviate your results, or it can make you either overestimate or underestimate your real efficiency of a system. For an example, apart from this, actually, people actually compute experiments in 3 modes, I would say, something like user studies, which people just behind the part chip, and the rest we're discussing MAB, A/B testing, etc. So user study is just something simpler. It's like I'm asking this cohort to analyze my recommendation systems, and while they are doing it, I'm actually tracking what they are doing. I'm actually logging everything that they are doing, what all actions they are doing, etc. Stuff like that. So we randomly select people, or not randomly, we actually select a group of people manually, you can say, for an example. And why user studies is an expensive thing as well, because you need, like, no one is going to do it for free. Users have this incentive attached to this overall evaluation, and then does the biasness kick in, because I actually want to make sure that I get that dollar amount paid, for an example. So I will actually act in a certain way so that their metrics looks good. Whatever they are tracking, it looks good for them. Apart from user studies, actually, it's not usually used as well, I would say, because it's a bit expensive in nature. You have your online experiments, and in online experiments, you usually talk about A/B testing. I'm not going to mention A, B because it's a bit complicated for my understanding. So in A/B testing, what people do is actually you just randomly select people and you show them a different recommendations from a different version of a made model or your variant actually. Something to note here is that you should actually just change one thing at a time, not multiple things. Otherwise, you will not be able to evaluate, is it that because of that very thing which you have switched or changed or tuned, that users are making more clicks, etc. Things like that. Apart from online experiments, we also have offline experiments, which is very common actually. Most of the people would actually use offline experiments. By offline experiments, we mean that there is this historical test data which is available in some DB, which you can query, and you take a snapshot of it. You do everything, your experiments and all that on the evaluation, and everything is done on that particular data set, which like historical data set, which we call it. But why offline experiment is also a bit bad, because by the time the model actually goes to the production, you can imagine that users' preferences might have just changed. We all are moody. We all are very moody, actually. So by the time what Recsys is thinking I'm liking, I'm just not liking that thing anymore. So that's one drawback of offline systems. And apart from all this, apart from all the mentioned topics which I've just mentioned, it's very easy to cheat, unintentionally, obviously, depending on how you are splitting your data. Like just like data splits is very important in any other ML system, it's very important in Recsys as well. How exactly you are overfitting, how much you are overfitting, so should we overfit, stuff like that. So apart from this, actually, let's come to the question that you have a model now, which is great. Now what you exactly need to do? Before we deploy it, we need to actually analyze, measure the impact, goodness of our recommendations, for sure. So there are some commonly used metrics, which I will just try to make it easier for you to, by explaining it in easier words. There are something known as MRR, then there is NDCG, which is nothing but normalized discounted cumulative gain. Then you have MAP, MEP, you have hit rate, etc. And sometimes you actually have your classically, like take the example of Netflix, for an example, Netflix movie rating, the competition which was there. So there people were actually trying to predict movie ratings. So there, when you have something like this, actually, you actually use something like an RMAC, MSC kind of metrics, or click value on an e-com as well. Apart from the traditional ones, these are like traditional metrics. Some metrics are very specific to business, and this will depend according to your business or whatever you're working on. For an example, recommended item click rates, FB send engagement metric. Basically, FB has this metric. I read it in some paper actually. They try to evaluate the user engagement every 10 days in a windowing fashion. Similarly, you could have it in 30 days, 90 days, depending on your needs. Apart from everything else, it is very important to always benchmark your new crazy model, I would say, or new super smart model, which you think, against something very similar or very simpler, something like BM25, or just like Eugene was mentioning here, most popular movies in a movie set, Recsys, let's say. Cool. So just one last question here before we go to the next slide. So what do people think that better performance with respect to the metrics? Does it mean better performance of the overall system? So what do people think? Is this true or it doesn't hold? Okay. So let's dive into precision and recall actually. So I'm pretty sure everyone is aware of what precision is, what recall is, but I will just introduce rank precision and rank recall. So rank precision is something like you're recommending K documents, right? So rank precision is what is the relevant documents in those top K documents, basically. What proportion of top K documents is relevant? That is rank precision. Apart from rank precision, you have rank recall as well, like proportion of the relevant documents which are in top K. Now, why exactly people use rank precision and rank recall? It's like one simple reason is that it's very easy to interpret. Like you can actually interpret it very easily. Now, why it is bad to use recall precision, things like that in Recsys, because they are very threshold dependent. Like if you change your thresholds, you just oscillate your thresholds kind of thing, and these things will go up and down. So there is a better metric actually you can use, something like that's why MEP was introduced, because now you get rid of the K dependency on the K. MP is something like mean average precision. So apart from this, actually, I just have this very simple tabular diagram for you to illustrate. So the red bars here shows that these are the relevant documents, and the white ones are basically the irrelevant one. And these are a stack of 20 bars, actually. So this is how basically precision and recall rank values looks like. So if you have 1 on 1, you have 1 and 0.5, stuff like this. Apart from this, actually, there is a very common metric which is used by everyone almost. It's something known as DCG. It is discounted cumulative gain. It has a weird mathematical formula here, but we'll come to that, no worries. So why exactly DCG was introduced or needed? If you will think about these two diagrams here, like, can you say that which retrieval is more preferable? Like, which one is better, the left side or the right side? Looking at the diagram, it's a bit hard to say that which is better because both looks very similar. It's just like one of these records got shuffled and we just shifted it to here. So we cannot say for sure. Precision and recall will not be able to tell you exactly which one is better. Apart from this, precision and recalls also assumes binary relevance. It's like this document is either very relevant or it is not at all relevant. So either it's a 1 or it's a 0. It's a binary hit. So DCG here comes in and it says that you can actually have multiple levels of relevance. By relevance here, we mean something like this. So let's say you are predicting 10 documents. So this is the relevance attached. So rank 1 document is very cool. It's the best actually. So we get a highest relevance score of 4. When the item which you are predicting is rank 2, we give it a 3. It's not that great, but it's cool enough to have it. Rank 3 also was great. So we give it a 4 score. This is what I mean by relevance. So here actually you can have multiple levels. So we have got rid of the binary relevance thing. Apart from the binary relevance, you can see the relevant documents with usefulness decreases rapidly with this rank. We'll come to this actually why it's happening. So this is how the formula of DCG looks like. So we'll come to this actually in the next slide. Let me just quick. We'll quickly switch. So here is basically the rank is. So this is what the relevance is, let's say, for an example. So what is this discount factor here? Discount factor is nothing but this log term here. So 1 by this log of 2 max of I comma 2. This is what is the discount factor. This I here is nothing but the rank actually. It's the ith rank, the first 2, 1, 2, 3, 4. That is what this is. Now, how do we compute gain? Actually, gain is nothing but you just multiply these two columns, like this column B here and column C here. So you will get your gains out of this. Now, once you have got your gains, discounted cumulative gain, how do you compute cumulative? You just sum the gains basically back on back. So 4 plus 3 becomes 7, plus 2, 9, then becomes 10. You have all zeros, so this stays here. And this is your DCG, final DCG. So you've got your DCG computed, very good. Like it's great. We have got our DCG computed. And hope I was able to explain as well. Now, what's the problem is DCG now. So people have actually used something known as NDCG, which is nothing but normalized version of the DCG. So as you can see, the DCG is actually not really bounded. This number can go anywhere. It can become very high or very low as well. So we will not be able to compare our queries. Like if you have 2 models outputting 2 different rec lists, by rec lists, I mean 10 different recommendations, we will not be able to compare them as such directly. So what do? We need to make it bounded somehow. How do you make it bounded? You just divide it by something. Now what that something is known as IDCGP. IDCGP is something known as like it's ideal DCG. By ideal DCG, it is known as the max DCG, which you can get if you are just using these 10 terms. So how can you get the max? You can get the max by rearranging the ranks actually. So all the good documents should come first. So all the documents which have rank of relevance of 4 actually should come on the first, and then relevance of 3, then relevance of 2, then 1, then 0. So when you do that, you will get something like IDCG, and then you can just divide it. You will get it normalized. Very good. We have computed NDCG as well now. What next? So is it that we just need DCG and NDC and we are done actually? Or there are some other metrics actually, depending on our use cases. We will see in the next slide actually. So let's say you are working at different places here. So different companies actually target different metrics. It's not like the whole Recsys systems evaluation can be computed on the basis of one metric. It is not like that. It's not going to work that way. For an example, Yahoo will use something different than eBay. YouTube will use something different than LinkedIn. Things like that actually. It's very difficult. So now apart from your recommendations, actually, you have used your metrics, you have got the statistics where everyone is very happy. What else do we need to track actually? Some things like we need to track is something like coverage, novelty, fairness, and diversity. There are confidence, robustness, serenity, scalability as well, but we will skip them in the interest of time. So these are very hard to measure. Once again, you actually need user case studies to do it. Not everyone is doing it, so it's less used, but that doesn't make it less important as well. It's quite important actually to measure all these things. So let's analyze one by one actually. We will analyze these 4 guys here. So let's just talk by coverage. What exactly coverage means? So from what I understand is coverage could be divided into 3 parts, let's say, something like an item space coverage, which is very simple, like what percentage of catalogs your recommendations are actually covering. So that's your catalog coverage, item space coverage, very simple. Apart from your item space coverage, what exactly is user space coverage? By user space coverage, I mean that for which proportion of users actually your recommendations are available. It's not just that I have just signed up on a website, let's say for an example, and I will start getting recommendations. Just like that, it will not happen until unless your recommendation is an online based system. So it usually takes time and you need to run your batch jobs, etc., to get the recommendations out for any new user. So apart from that, how can we actually measure like for which users to show the recommendation depending on the richness of the user profile, I would say. So if a user is having good amount of metadata or something which we actually need, then we can just show them. So something to compute could be user space coverage. How many users we're actually covering. Apart from this, I would say that cold start, I mean, everyone has discussed, so I can just skip cold start problem, but it's like, how does your system behave when it interacts with new users or items? Apart from all of this, actually, there is this cool long tail thing which exists, and Recsys actually exploits the long tail. So why does Recsys exploit the long tail? You can imagine that the user's experience would be very bad if your recommendation system keeps on showing them items from the right side of the tail, actually. So these items are not very popular here. The one in the green, these items are not very popular. They exist on their long tail side. The popular items are actually here on the bluish curve. And how do you say that? Like, how do you draw this vertical line, actually, like which threshold you cut the graph to say that this is popular, this is not popular? That again becomes an hyperparameter. You need to figure it out how it is. So user experience actually will ruin if Recsys keeps on showing items from the long tail, which is not something we want, because we want our user experience to be great. So that's all about a coverage, actually. Let's talk about novelty. What exactly novelty means here? So novelty is basically, we want our results to be as diverse as possible because it helps in the business retention of customers. I will just give you a very motivating example. So let's say you're watching YouTube videos. We go and watch every day. So depending on that, is it that your Recsys should keep on, like the YouTube's Recsys should keep on showing you the same video again and again, or you would actually prefer something out of the box, actually, which you are not expecting for the system to show up to you. So this is what actually novelty means. So your users should actually be surprised with, like they should have a surprise element in it. And why it is good? It is good for your business because your users will actually stick to your system and not switch to any other system out there which they are using. How do you boost it? Just like Goku was mentioning that people use Bloom filters, actually, you can actually use Bloom filters here as well, so that you will actually remove some of the items which the users have already interacted with, so that you can make up some space for random items and new items. Apart from that, actually, let's talk about something like, which I like, which is fairness. So fairness is like, it's very dependent on context and it's dependent on application. So how you are using and what do you mean by it, it depends. So let's talk about it. So a typical Recsys system actually exploits rich gets richer characteristics. So what do you mean by rich gets richer? It is very simple. It's like something which is very popular keeps on getting popular more and more as time passes by. Then comes a point, actually, after which its popularity decreases. But until that time comes, actually, the uncertainty of the item, whether we can say that it was good or bad, has already decreased now. So what do we mean this? We mean that like context being popular, like which is very popular, are favored more over new content creators, which is very bad because let's say tomorrow, let's say you're publishing a video, that this video which you're recording right now will get published. So if we don't get viewers, actually, it will just discourage us from publishing it again or making or having something like this session again, right? So why do you think actually most Recsys relies on social reputation links? The answer is very clear, actually. The risk associated with the recommendations, it's very much lower, actually, because if your recommendation system is basically, what should I say, is recommending items which are very popular, the uncertainty of the item, whether it is good or not, is very low now. So your users are not likely to churn out, I would say. It helps in user retention. And apart from this, actually, if you're using social links, it's very easy to explain your recommendations as well. It is like, I'm showing you this recommendations because you are following this person, that person, etc. Something like this. I will take a motivating example as well as to how TikTok does this. I mean, TikTok was very famous when they introduced their flywheel, actually. So how does TikTok does it? It's basically just to give an intro to TikTok. If people are not aware, it's a video sharing platform, short video sharing platforms, and your every content actually gets your full UI screen view. By UI, I mean if you're holding your phone or tablet, the video will be in full screen mode. So if you can imagine that, and there are a lot of people actually publishing videos. Every now and then you will find different videos being uploaded. So how do you introduce fairness to your Recsys system? So we'll just discuss how they did it, actually. So this is actually the diagram here. So whenever a new video gets introduced to your system or it gets added, what they actually do is they put it in buckets. So if a new video is put in this bucket, let's say, all the videos will go there which are new. So this bucket is basically something which is less than 50 watches. So once the watches increases, you keep on going down, down, and down, and down. Basically, the popularity of the item increases down the buckets. And so is the probability of selection. What do you mean by probability of selection? Let's say you're trying to recommend a new video to a new random user. So you can actually select a item from this bucket because you for sure know, or you will select some of the random slices. What random slices mean? Random slices is nothing but cuts of the video actually. You just select one of the cut and you can show it to your user. You know that this is a very popular item, so the user is most probably going to like it. And at the same side, actually, if you have a very heavy user, which we are calling by heavy user, I mean someone who uses these platform too much actually, we can actually judge them on lesser popular videos. These videos, we can actually show them these videos. They're not likely going to be irritated or something. They will just skip it or swipe it or do something like that. Cool. So let's go to diversity. Now, what do we exactly mean by diversity? Let's take again an example of a Netflix account being shared with your family, friends, like password sharing or whatever it is. We usually do that thing. So is it a problem for Recsys actually? Why not? I would say like it is actually a problem from Recsys because let's say in your family, you might be the one who is watching a lot of content, sci-fi content. So your recommendation system would actually start showing you recommendations, just sci-fi movies. It will not take into account other users who are actually viewing or sharing the same account. So dominance becomes a problem. Otherwise, then there is another problem is generality, basically. Generality, sorry. Two general items, basically, not directly related to user-specific taste. So what do we mean by this? We mean that if let's say 4 people are sharing a Netflix account, then now actually different people have different tastes. So the recommendation system will find it very hard to give you actually a personalized recommendation, so to speak. So generalizing now it showing something general movies, something like an Interstellar, which is all time famous. Just for an example. So here actually, like, how do you do care? So by using items different, for an example, way to compute the data, we can do that for sure. Apart from this, we can use user groups actually. So measure the diversity based on users method as well. Simply put, diversity is the Rex spectrum of your recommendation system here. Spectrum, we meant that what are items we are recommending to our users. So that's Rex spectrum.
Aditya?
Yeah.
Sorry.
Actually, let's just talk about our takeaway. Yeah, hello.
Can you turn off your
video?
I can hear your voice is very choppy.
Hello.
I think you have like a poor connection now.
Hello.
Hi, Aditya. Sorry, your voice was choppy. So can you maybe turn off your video and like just...
I'm sorry for that.
No worries, no worries.
So it was choppy from diversity section or which one?
I think you were in diversity, like midway.
Okay, let us go ahead with diversity again. So I think we have discussed this TikTok section for sure, how TikTok takes care of the fairness for the newly added contents. Like we need to do that for sure.
Sorry, again, you're not sharing your screen now.
I'm not sharing my screen. Okay, yeah. I'm sorry for that actually.
No worries.
Very sorry, very sorry. Cool. So we were here actually last time when I was talking about how TikTok takes care of newly added content users or something like that. They actually trickle down every new video to buckets, and then they randomly select which, like they randomly pick one item from each bucket and show it to the user, depending on whether they are like heavy user or they've just come to the platform, things like that. That's how TikTok ensures fairness in their system. It's one of the ways. Apart from fairness, the last one which I would highlight is diversity. So let's take for an example that we are actually using a Netflix account with family or friends. So it's a shared account. So now, since you're using a shared account, would this be a problem for recommendation systems? Yes or no? It could be a problem because your Recs could actually be dominated by just one person, depending on whether that person is the heavy user in that account. Otherwise, what will happen is your recommendations will just be very general. It will be nothing very specific to one's user tastes. So that is also another problem. Now, how do we know that how different the Recs are actually? We can actually measure the diversity based on items metadata. By items metadata, is it something like one recommendation is from sci-fi, the other one is from romance or thriller or horror or something like that? Apart from this, actually, can we actually figure out are the user groups interacting with each other different? So how do you know that? we need to again look into the user's metadata to figure that part out. Let's say the user's age group, what kind of movies they have watched in past. So what kind of movies should we predict them? Something like that we can take into that account, and we can analyze basically, was the rec which was shown to the users good or not? Simply, I would put diversity in one line. It's something like it's like the rec spectrum of your Recsys. What exactly are your recommendations? What all recs you are showing to your system? That's it, I would say, and it's a final slide here. So some key takeaways from all the sessions, I would say. Whenever you're starting with Recsys, I would say have a clear objective, write it down. It's a pretty vast space and very easy to get lost in this dimension. It's very easy, actually. Something like simple thing is, it's better to start with no ML, actually. Just use a simple SQL query, just top key items. It will work great, actually. Until and unless you can get a good baseline for your Recsys. Apart from this, set your training infrastructure early, just as Goku was mentioning all those training infrastructures. It's actually very hard to connect all these things together efficiently. So make sure that you have your infrastructure set up properly, because if you have your infrastructure set up correctly, things like data pipelines, ETLs, they will become much easier to do. I mean, whoever the person is working on the system, it'll be much easier for them. Apart from this, think about evaluation from early days. It's very important and it's usually ignored as well. You should set up your baseline model, something like BM25, TF, IDF, things like that. And you should ensure their correctness as well, because you need quick iterations, right? And in order to get quick iterations and increase the developer's velocity, they need to evaluate it with something, right? Let's say you have come up with a model A, you need to evaluate it model A dash, model B dash. So if this pipeline is set up, it will be much more easier to read because we don't get results in just one experiment. Like Recsys is actually
Sorry, Aditya. Your voice is so choppy today.
It's very important. Data is some.
Aditya, if you can hear us, the signal is choppy again. I mean, it's good that it's happening here.
I'm audible now?
So you stopped sharing and it's a little bit better now.
Okay, cool. I just stopped sharing. So I would just give my key takeaways actually on this slide.
Okay.
So it's very important to have a clear objective.
Yeah.
Like it's from your day one, actually, it's very important, because write it down if you want. Recsys is a very vast space and it's very easy to get lost in this dimension. Apart from this, actually, just like Goku was mentioning, it's very important to get your training infrastructure correct as well. Something like if infrastructure is correctly set up or it's very easier to access, your data pipelines will be running very quickly. You will be able to do your ETLs, you will be able to do sampling, label strategies, etc. pretty easily. Apart from this, it's very important to think about evaluation from early days. By early days, I mean right from your day one, actually, when you're starting to onboard a Recsys system, it's very important that you start thinking about evaluation from that point of time. A very simpler way to do it is set up baseline models upfront. It's very important that you share, like you have ensure the correctness and set up some simple baselines, which are pretty hard to beat, I would say, for any Recsys system as well. Apart from all of these, it's very important to have humans in the loop for subjective evaluation. Like time and again, actually, you should just pick some users or just pick some recommendations and just check it out, actually. How is it, like, does it fit if you were in that shoe? So something like that. Apart from all of this, you need to check in for biasness in your evaluation, because as humans, we usually get biased. So it's very important to watch for that. And apart from all of these, there are some things like sensor content, spread positivity, user privacy, which you need to account for. So yeah, that's a wrap. So with that, I would just mention a lot of references on these slides. There are a lot of these cool links here, which you can go through. And there are some implementations I have attached, which you can look as well. So, and finally, like we would wait for all of you to join the jam session, which will be taken by Amar and Jacoby actually on June 19th. So yeah, looking forward to see all of you guys there. And apart from that, Thank you very much for listening to me and rest of us. And apologies for the internet instability.
No worries. Thank you so much, Aditya. I believe there are a couple of YouTube questions that are coming. I'll share them here, and if you want or others want to answer. One is, how do you handle data concept drift? It's how to tackle unseen events like COVID-influenced hiring. And the second part is another message. In evaluating recommender systems, do you do weekly deployments on new data?
I'm not clear actually.
I guess the theme is like, how do you handle when things start shifting? Like COVID started and then recommendations would change at that time.
We definitely need to wait for the COVID to collect some data. It's like all the systems were broken when COVID hit. None of the systems was trained for something like that across the whole globe. So everyone waited for that data to accumulate, and then definitely you need to do a deployment for sure. If you want to account for COVID-like systems, like it was new for everyone across the globe, right? No system actually knew the word COVID as well before COVID. So if you want your ML model or your Recsys to know, you definitely need to retrain it and redeploy it. You can do shadow deployments if needed, but shadow deployment is something which is not usually done in Recsys. Yeah.
So in my experience, yeah, always be deploying. Yeah.
Yeah.
So in my experience, when COVID hits, we notice a sharp drop, 9 click-through by InConvert. Our data was 2 weeks. We have a 2-week delay for data, right? So we noticed a sharp drop in convert, and pretty much we just have to throw the model out, existing model out, and roll back to a rule-based system. So like for conversion modeling, we have a model, right? And then we have a fallback model that's basically just take the moving average of past X sessions or past X days. So we just throw the model out, roll back to baseline, and just use that until we gather enough data to retrain the model. It was crazy. We have to retrain the model from scratch for both click and convert model. And I think it's different for everyone for sure. And the use case is going to be different. Some e-commerce shops that's big, I know that they do retrain the model. They do retrain the model. They do repopulate the recommendation table on an hourly basis. So that's another way to handle that. So always be deploying if you have the data, because most people might not have immediate feedback. If it's clicks, you're gonna get it. If it's not clicks, it might be delayed. So depending on which subject or which metric you are trying to optimize for, it's going to be different.
Awesome. Thank you, Han. The other question here, I think it's a very good question. So when we talk about fairness, I think most of the talk was about diversifying and giving the equal chance, at least like to new people and popular people.
Yes.
But does it also tackle the like ethical stuff? Like, for example, say one YouTuber is has toxic content. Does that fall under fairness, or does it fall under maybe something else like filtering? Or
if it's a toxic content, then actually it would be better that it's filtered out of the system, I would say. Usually things which go viral are the ones which get more clicks or more hits. It's very common with any social system. But if you will watch it carefully, that videos actually gets taken down by the system once they detect it as well over the time. It will not happen right now, but I would say that it depends. But content moderation is definitely very important, and it is under fairness for sure. It's not under diversity, because you definitely don't want to show something like that to any user. Like there should be as minimum negative user perspective as possible in your system. I would say in the point of view of your human health, mind, presence, anything else, it would be better that you can do content moderations. You should actually have very strong content moderations.
Right. I think one relevant thing to that is like I think Facebook did something last year where
voting things.
Like posts that are more clickbaity. Well, it's not on moderation toxicity, but like posts that are clickbaity, they were getting like lower scores. Do you think that also falls under moderation? Like, for example, pages where learning that certain content gets a lot of clicks and people just go to that post more and more, when it has like zero value for the audience. So I remember they said something about pages that use those phrases that are just clickbaity, they will get less scores from now on.
I would say that I would not mix fairness with content moderations, just like everyone is saying, but it's a very separate topic. Fairness is something that everyone should actually get a chance to shine. That's what TikTok was doing. Like if I'm a new user, I should get a chance. If I'm a famous person, I should also have an equal chance. So that is what by fairness I mean. Like everyone should get a chance to shine on their own. So yeah.
It's a very good answer. I don't have any more questions from YouTube. One personal one that I have is, do folks here have any thoughts on those, what is it, recommender system as an API? I think AWS has one, several startups have come up with one where they either like are directly to consumer or they integrate with company systems and they try to give them an API that they can call against. Any thoughts on those?
I'm not sure actually how exactly it works. Like I'm just saying my views, because in order for Recsys to work, you will be sharing your data with them, which every company might not just be okay to do that. So if you're asking Apple for an example, they are very user-centric, privacy. They are never going to do that for sure. So they will never use something like a Surface. But for an example, if there's a startup which actually doesn't want to spend a lot of time in building a Recsys, so yeah, why not? I will just use a service which already exists. So I can actually focus on something like user growth and my market for now. And then I will come back and take that from them. And then I will create my own Recsys. Something like that, I would say.
Great point. Yeah, I don't have any more questions myself. If anyone else wants to ask something, go ahead.
This is Anji, just getting back to this fairness question, right? Just to be fair, if we start showing, if TikTok starts showing subpar or not toxic, but bad quality videos, right? To be fair, right? Then that reduces the overall effectiveness of the platform. So how do we balance these two?
It's a pretty hard question, actually. Because like a user, like just like I said, TikTok is actually placing a lot of bets in every single prediction which they are showing to our user because of their UI, for an example. How do you actually prevent your users from not churning? I mean, that's something I need to think on, actually, NG. It's a great question, actually, for sure. Like others can share.
Like, so if we talk about fairness, there are several definitions, right? And everyone's definition could be slightly different. Generally, there is going to be like a few categories. One is like from my not so fair memory. One is anti-classification. So you don't want to classify your users by race, gender, blah, blah, blah. Or in Aditya's case, you don't want to classify user by certain piece of content by popularity. So that's one way to classify. That's one way to measure fairness. And then there's probably other things like you want classification parity, right? You want parity, like whether I think equality or equity, so to speak, right? So let's say, for example, you want new users' content to be surfaced as much as old users' content or like superstar user content, right? There's classification parity, right? So there's usually like this anti-classification versus classification parity. Maybe there's a few more type of definition of fairness that you would have to think about. So So it really depends. And at the end of the day, it's going to be who is the boss and who judges like which KPI you want to measure against, right? And sometimes anti-classification versus classification parity, that might be conflicting against each other. And that's just, I don't know, maybe sometimes it could be too, I guess, it's above my pay grade, so to speak.
That's a great way to say out, actually. Yeah, cool.
And yeah, and also you can, there's the other way is like what Eugene and you were mentioning about like content moderation, right? Maybe that's calibration, maybe that's content moderation, like how do you ensure all those? So there's a lot of facets to like just a simple word, fairness. It's not how it's so there's not, I don't think there's a very straightforward definition like recall or precision. Right, so there's many different definitions of fairness, and how to optimize for that. It's going to be quite different.
It's a hard question. Yeah, but yeah, it's a great answer as well. I mean, it depends. Unless you're actually dealing with something like this, it's very hard to think in that train of thoughts as well. So. Cool.
Yeah, fairness is so subjective.
Like these things actually don't have a definition. I tried looking up a definition, but I couldn't find it. So I just created my own. So you can say that.
And I think specifically in the case of the TikTok recommendations, right, where, you know, if you have a quote heavy user or a super user, I feel like they're very unlikely to churn if you show them one bad recommendation if they're on like the 25th page of scrolling. You know, and it works to your advantage really, because like no one else is going to be looking at that new content, right? But you need that novelty. So I think that that's actually a good thing, because your odds of the customer churning are extremely low at that point, right? Like if I spend half my life on TikTok, I'm not just going to walk away because I watched one thing that I didn't like, because odds are you've probably already seen millions of things you didn't like on TikTok, but you're still there anyways. Right. It's kind of like the same thing with Twitter, right? Like I'm sure everyone understands the idea that Twitter gives you brain damage, yet, you know, people can acknowledge that and still be on Twitter all day. So I think that your odds of failure are quite low once you start hitting those super users, and you can start milking them in a sense.
Wow. That's one way to see it. Before more people start dropping off though, I just want to remind people that for the jam session, there's going to be more opportunities for breakout and discussions, and it will not be live streamed or recorded. So we hope that you will stay with us next week.
Okay.
I'll end the stream now on YouTube. Thank you everyone who tuned in, and if you want to keep discussing